So the example says that warm, dusty, moist air composed of 6000 kg of air, 200 kg of water and 0.4 kg of solid moist aluminum oxide powder, and this is moist, so we have 18.75 weight percent of water is there, and this is at 50 degrees centigrade and 0.97 atmosphere pressure. It has to be processed through the electrostatic precipitator. The logarithmic particle size distribution of feed particles is provided. You have to use the ideal property method. You are asked to simulate the USP process fabricated with two numbers of 5 meter cross 5 meter plate using the Crawford efficiency calculation and dielectric constants of the mixed feed and solid feed, they are given. Okay, so the problem is quite straightforward. Let us try to solve it. And first we have to go to the properties and we have to fix the components. First we have to fix air, water and Al2O3. This Al2O3 will be solid. Okay, and we have to use ideal method, run it. Okay, now go to the simulation. Now first go to the stream class, use mix CL PSD, go to solid, and we have to fix the particle size distribution mesh. Now it is said logarithmic PSD of feed particles is provided. Now I have those information in an Excel file. So this is logarithmic, so that much we know. So it is logarithmic, but we have to find out the number of intervals and the limits. So limits is very easy. It is 0.001 to 2. So 0.001 to 2, but how many intervals are there? It is 101 minus 1, right? 101 minus 1. So it is 22101. So 100 intervals. So 100 intervals between 0.001 to 2. Right. So we will keep it as 0.001 to 2, and they are saying it is in millimeter. 0.001 millimeter means it is 1 micron. So from 1 micron to 10 micron, so around it is about 95 micron. Okay, but what is our range? Our range of operation will be around 10 microns. So it is in the higher range. So I do not know whether it will give reliable result. Actually, we should work with some material with 0.01 to 10 microns, but here we find it is going up to around 95 micron. Even if we do not consider them, at least it is going up to 70 micron or so, right? So, okay, let us continue and see what happens. So it is 2 millimeter and 100 intervals, right? Create PSD mesh. Now let us go to the stream. First, let us rename the stream. So it is feed stream, it is gas stream, and this is solid stream. Now feed stream, the temperature is 50 degree 0.97 atmosphere. So it is 50 degree and 0.97 atmosphere. And the moist air is composed of 6000 kg and 200 kg. So it is 6000 kg and 200 kg. Go to solid, there it is 50 and 0.97 atmosphere. It is 0.4 kg of weight 18.75 water. So it is mass flow rate of 0.4 kg and mass fraction. Okay. Now, as we have the water component in it, so we have to define some moisture over here. So we have to go back to the solids, and there we have to define water as the moisture component. Then only here you can find the moisture. Yeah, now it is possible to give the mass fraction, which is 0.1875, and this will be 0.8125, right? Yes. So that makes it 1. Now the logarithmic PSD we have already set. Now we have to provide the data. And this data is there already. We have over here. So we will just copy it and paste. Copy and paste the values. Yes. So we have fixed the weight fraction. So feed is defined. Now let us go to the problem once again. Simulate the process fabricated with two numbers of 5 cross 5 plate. So we have to go to the input, and there we'll choose a plate type, the simulation and Crawford. So it is 5 meter cross 5 meters. So it is 5 and 5. There are two number of plates. So we give 2. And we have to provide the dielectric constant, which are 80 and 10.6 respectively. So for mixed feed, it is 80. For solid feed, 10.6. So this is 80 and 10.6. Okay. So these things are all default values. We don't change them. We run the process. Okay. So the process is run. We can check the results, the stream results. So the mass flow rate, we can check the solid takes up 0.325. So the gas stream has very little amount of, negligible amount of solid. Almost everything is going to the solid stream. So we expect that the separation efficiency will be very near to 1. The separation efficiency it's 1 only, because the gas stream has negligible amount of solid component. And the gas velocity is 1.45 meter per second, so it is within 1 to 2.5 that is required. And power requirement is 0.4 kilowatt. The total width of the precipitator is 0.228, and pressure drop in millibar, it is very small, so it is only 1 millibar pressure drop. And the separation efficiencies, you can check for different particle diameters what are the separation efficiency. Practically they are all 1 only. And the stream result, if you want to see the particle size distribution, you will find that the particle size distribution of feed and solid, they are almost same. And only very fine particles are going to the gas stream. Otherwise, everything is going to the solid stream. Okay, now let us go to the second problem. It says the ESP has to be designed for 99.5% efficiency. So it says that it doesn't require 100% efficiency. Probably it is going to the over design mode. So let us design it for 99.5% efficiency. That is enough for us. So we have to change the input specification. For that, we have to make design. Separation efficiency has to be 0.995, that is 99.5, and all other parameters we keep same. The operation options, dielectric constant, and some new design parameters have been given, like gas velocity, maximum height, maximum width, etc. So we keep them as it is. So let Aspen design the ESP based on whatever the default values it has taken. Now let us run the process. Now let us see the results. Gas velocity is 2.07 meter per second. It is also within the range of 1 to 2.5. And then it needs 4 plates. And the plate height and length both have reduced because we were using 5 cross 5. Now it is saying that, well, if you use 1.1 cross 0.87, that is sufficient for overall collection efficiency of 99.5%. So why to use a larger plate unnecessarily? The power requirement is same as before. The solid concentrations and all, they are also same. Let us see the pressure drop. Pressure drop is 2 millibar. Pressure drop is 2 millibar, 2.04 millibar. Earlier it was 3 millibar, right? Now it is 2 millibar. So pressure drop also has reduced. So that is how we design the ESP for Crawford calculation method. The next problem is redesign the ESP for 99.5% efficiency using Deutsch efficiency calculation. So from Crawford, we come to Deutsch. Now, here you have to use some extra segments, like 3 segments. The loading and precipitation area voltages are given 90 and 10 kilovolt. They are required data. Take the gas velocity function as 3 plus 4.7 v plus 5 v square. You might remember that the same function we have used for fabric filter as well. So you can repeat that function where the velocity is in meter per second and pressure drop is in millibar. Okay, so let us design it using Deutsch method. In the Deutsch method, you have to use 3 segments. Nothing has been said about the exponent k, so we leave it as 1. The number of segments, we'll use 3, that is required. And the loading and precipitation area voltages are 90 and 10 kilovolts. So we will write 90 kilovolt and 10 kilovolt. Right? And gas velocity function is delta P is equal to 3 plus 4.7 V plus 5 V square. So we have to go to the operation options, and here we have to change. So we have to change the gas velocity function. Pressure drop unit is in millibar and velocity unit is in meter per second. And then 3, 4.7 and 5. So we write 3 over here, 4.7 over here, and 5 over here. So that's how they have been specified. Now run the process and see the results. The gas velocity is coming down to 0.45. Now you might remember the gas velocity has come down below 1, but for Deutsch and Swarovski model, your range is from 0.15 to 5 meter per second. So their range is higher. So it is still within the range. And in Deutsch model, the number of plate has increased from 4 to 7. The plate height and plate length also has increased. Power requirement has slightly increased. The total width also has increased. And the pressure drop also has increased to 6 millibar. Okay. So it is on the higher side in the design. Now go to the next problem. It says redesign ESP with tubular model. Now we change from plate to tube. Having 2-inch tube radius and 1 millimeters spray electrode radius. Pressure drop may be calculated from dynamic pressure. So we will go back to the input. Here you will use tubular model. So from plate type to tubular type. So a few extra information needs to be given over here. So 2-inch tube radius and 1 millimeter spray electrode radius. So 2-inch and 1 millimeter. Okay. And pressure drop may be calculated from the dynamic pressure. So we go back to this one and run the process. Okay. Now see the results once again. So here also see gas velocity is below 2.5. So it is within the limit. Then power requirement has increased threefold. Earlier it was 0.445 or so. Now it is 1.49 kilowatt. The pressure drop has decreased to 2.8 and number of tubes are 84. 84 tubes. So tube length and tube radius have been designed and the total precipitation area is 21.09 meters square. Okay, so this is what we get by using the tubular type of precipitator. Then the next problem is simulate ESP with Swarovski model. You have to take 1 meter long 80 number of tubes with exponent alpha is equal to 0.5 and pressure drop 3 millibars. So in this case, we have to go back to simulation mode. So simulation with Swarovski, exponent is 0.5. So instead of default 0.53, we take 0.5. Tube radius and tube length. So tube radius actually it is 2 inch and spray electrode radius is 1 millimeter. But new information is 1 meter long and 80 number of tubes. We are fixing the number of tubes because it is a simulation problem. Okay. So 1 meter long tube, 80 numbers of them. So 1 meter long tube and 80 numbers of them. And the pressure drop is constant at 3 millibars. So we will go back to operation options and we will make it constant at 3 millibar. Okay. So that completes our problem formulation. Now let us run the process. Okay, so it is available with error because I failed to give it to 3 millibar. Run it again. Now the results are available. So this is a very quick proof that if you give a junk input, then Aspen Plus will fail. So through this simulation, we find that gas velocity is greater than 2.5, but it is okay because it is Swarovski model, so our range is from 0.15 to 5 meter per second, so 2.55 is well within the range. The collection efficiency has reduced from 99.5 to 97.9. Power requirement is more or less same and the pressure drop is 3 millibar. These are the things that we have ourselves fixed, nothing to see about that. Okay, so this is the simulation problem and we will keep this particular thing and we will change it to design and look at it later. So let us keep it over here. Next problem says change to design model and analyze the results. So we will keep everything same, just make it design instead of simulation. Okay, so run it. Now see the result and compare. So gas velocity reduces with overall collection efficiency increasing. Power requirement is same. Pressure drop is same. But the number of tube increases. Okay. Here you were happy with 97.9% of overall collection efficiency with 80 number of tubes. But in this case, you are asking for higher efficiency. So higher number of tubes are also required. Then tube length is 1.8 in place of 1 in the simulation case. So in order to have a 99.5% efficiency, you have to use a longer tube. That's what it means. Tube radius is same as before, and the precipitation area, it is 113. So it has increased more than 4 times. Okay. So that is the direct comparison between a design problem and simulation problem with various data compiling together. Okay. With that, we come to the end of this lecture. I hope you have enjoyed it, and we will come back with yet another interesting lecture very soon. Thank you.